awkward. Okay. Our next section is 10.2, which is technically talking about circles and ellipses. Now, we're not going to dive into circles because it's really the exact same conversation we had in 1.1, but just as a refresher, remember a circle has the format x minus h quantity squared plus y minus k quantity squared equals r squared. So the center is hk and the radius is r. So section 1.1, go back, watch the first video if you forget. The whole idea with the circle is from the center, if you radiate out in the same distance all the way around, that forms a circle. But for an ellipse, what happens is you have two lengths. You have a longer side and you have a shorter side. So for the rest of this section, we're only going to focus on the idea of an ellipse. Without going into it greatly, as far as the derivation and all that stuff, an ellipse, the idea of an ellipse is that, actually, let me just sketch one out here real quick. And in fact, I'm going to purposely write an equation here so you can sort of start to match concepts together. Suppose we had the equation x squared over 49 plus y squared over 16 equals 1. Now, that's an equation of an ellipse. As far as what it's saying, we'll dive into that. I just want to have this discussion based on a picture. So this ellipse will be 7 units out from left to right. Oh my gosh, this is awful. And then 4 units up and down from the origin. So 7 units left to right, 4 units up, down. We already know about h and k. hk gives us the vertex for a parabola. hk gives us the center for a circle. hk also gives us the center now for the ellipse. H is always with x, k is always with y. And notice for this one, we're not subtracting anything from the x term. We're not subtracting anything from the y variable, I should say, which means that our h and k are both 0. So that makes our center 0, 0. But unlike a parabola and a circle, we have 3 new letters involved. The first letter is A. A is the distance from the center to the vertex. A is the distance from the center to the vertex. Your vertices are the endpoints of the longer part of the ellipse. So we have a vertex here at 7, 0. And we have another vertex here at negative 7, 0. Because our center is at 0, 0 and one of the vertices is at 7, 0, that means the value for A is 7. These other 2 points, namely the one that we want going up and the one that was created going down, technically do not have a name in mathematics. Just so there's no confusion, I don't want to just say those other 2 points. I'm going to refer to these as the covertex. So notice we have a covertex at 0, -4, and a covertex at 0, 4. And we define the letter B to be the distance from the center to the covertex. So if you know where your center is at, and if you know how it's positioned, either an ellipse this way, which we would call horizontal, or an ellipse this way, which we would call vertical, and you know your A and your B, you can draw your 4 points necessary to create the ellipse. Now, let's look at the equation, because we really didn't reference that just yet. X squared over 49 plus y squared over 16 equals 1. Where, by looking at that, would you know, or would you think A would be 7? What do you think is going on with that equation that says, hey, A is 7?
You would take the square root of 49.
That's correct. That was a weird audio clip there. Yeah. This guy here is actually A squared, which means A is 7. And likewise, this right here is B squared, which means B is 4. So notice the equation, just by looking at it, tells us, hey, you're centered at 0, 0. Again, you're not subtracting anything from X, you're not subtracting anything from Y. It says A squared is 7. I'm sorry, A squared is 49, which means A is 7, and B squared is 16, which means B is 4. Now, couple of comments. 1, for an ellipse, A must be bigger than B. That is only true for an ellipse. The reason I'm saying that with highlight it is because we're going to have the same definition of A and B in the next section, but there is no relationship between A and B in the next section. This relationship is only true in this section. That's comment 1. Comment 2, the thing that gives away if it's a horizontal or a vertical ellipse is actually the location of A. If the larger number is underneath the x squared term, like we have here, 49 is bigger than 16, that makes it horizontal. So if the larger number is underneath the x term for an ellipse, it makes it horizontal. As you might guess, if the larger number is underneath the y, then it's vertical. Now, on your final, you'll be given a formula sheet just like this, which will have, so we talked about the parabola ones last week, and we're talking about the ellipse and hyperbola ones this week. And notice we have basically this first formula here explained but not yet written down. That's where we're about to head to. You don't have to worry about memorizing the formulas. You'll just have to remember what they mean. So remember, for an ellipse and hyperbola, A is always bigger than B. And the location of A dictates if it's horizontal or if it's vertical. The last little part of the ellipse, that even though we have the graph there, the real reason this graph is existing is some two other points called the foci. The foci are given by the letter C. C is the distance from the center to the focus is singular, foci is plural. I can't spell plural. There we go. For reasons we'll get into later, the foci are like, I think for this graph, I don't know. This is hard to do in my head. Foci are like around here-ish. You'll see why in a second. So there's a focus, there's a focus. And they are the ones that actually dictate the shape of the graph, nothing else. What happens is, for any point you pick on and this is the definition of ellipse. We're not going to write it down. It's in the book. But the whole idea is, for any point you pick on an ellipse, if you found the distance from that point to each foci and added those distances together, you're going to get a number, whatever that number is. And the idea is, no matter what that number is, if you picked any other point and found the distances between the foci and added that together, it's the same number. So you may have seen before in your life where someone puts like two little push pins and they put like a rubber band and they like drag out a pencil so the pencil is going around and the rubber band's getting caught on the push pins. And if you do that, it actually creates an ellipse. Those push pins are the foci in this example. And so you're keeping the string taut and it creates an elliptical shape. So the big takeaway again is, I have no idea. So I'll just say, let's move on into the formula. The formulas for an ellipse. We'll do some examples. And again, now we have 5 letters to find: A, B, C, H, K. Okay. Let me add a slide and we'll do that next. Okay. Ellipse. So we'll come back to this slide a couple times. We have 2 types so far. We have a horizontal and a vertical. The equation for and I'm going to put here centered at origin. The equation for the horizontal is x squared over a squared plus y squared over b squared equals 1. And the vertical, x squared over b squared plus y squared over a squared equals 1. And again, the huge thing is, for an ellipse, A has to be bigger than B. So if the bigger number is underneath the x term, it is horizontal. If it's underneath the y term, it is vertical. And then the only thing we're missing is how to find C. C is C squared is equal to A squared minus B squared. And again, that formula is also given to you. I don't want that. Okay. So let's do an example. Suppose we had x squared over, oh, these are very hard. X squared over 16 plus y squared over 25 equals 1. So to contrast this to a parabola, one variable was being squared. For our purposes, that's enough to say, hey, that's a parabola. For an ellipse, if two variables are being squared and there's a sum in between, then that makes it an ellipse. So walking through this, a squared is the bigger denominator. What is our a equal to?
5.
Excellent. B squared is the smaller denominator. What is our b equal to?
4.
Excellent. C squared is a squared minus b squared. So off to the side, c squared would equal a squared, which was 25, minus b squared, which is 16. 25 minus 16 is 9. Now, technically, we're about to take a square root of an equation, but c is a distance, so we don't include the negative, we just include the positive. So we would say c is 3. And notice we're not subtracting anything from the x, not subtracting anything from the y, so our h and k are both 0. Questions on these 5 letters? Okay. Is this horizontal or is this vertical?
Vertical.
Vertical, good. The bigger number is underneath the y, that makes it vertical. So because it's vertical and because our center is at the origin, I'm just going to put a C there to say, hey, center. We're going to move vertically a units away to find the vertices. Since a is 5, that means we're going to go up and down 5. If we go up 5, that gives us one vertex at 0, 5. And if we go down 5, that gives us another vertex at 0, negative 5. So again, A is the distance from the center to the vertices. B is the distance from the center to the co-vertices. We move in the perpendicular direction. So the co-vertices for us will be left and right. So if I go left 4 from the center, that would be negative 4, 0 as one co-vertex. And right 4 would be 4, 0 for the other co-vertex. At this stage, we could draw the oval. I'm just going to throw in the foci first. Just like a parabola, the foci are always in the curve. So we had a parabola and the focus was sitting inside. Same idea, your foci have to be inside of your ellipse. And what that means is they are always in the same direction as A. Since we are vertical for our vertices, that means our foci are also vertical. So we're going to go up and down 3 units because C is 3. So if I go up 3, I get one focus at 0, 3, and down 3, I get another focus at 0, negative 3. With all that goodness, we can connect our 4 points, our 4 blue points there. It's not going to look good. Oh, no. Oh, that's lumpy. I think that's a potato I met once. All right, that's good. Side note, the numbers aren't always going to be pretty. I purposely picked a Pythagorean triple, 3 squared plus 4 squared is 5 squared. You might have ones that have radicals, and you can see those in the example videos, so definitely watch those. But for the purpose of just introducing the material, I'm picking nice and pretty numbers. Okay. Now the other half is, what if we're not centered at the origin? I'm going to go back a slide now. If we're centered at HK, just like parabolas, just like circles, H is always with X, K is always with Y. Oop. Okay. But the same rules apply. Bigger number underneath the X, horizontal. Bigger number underneath the Y, vertical. So let's suppose we had x plus 2 quantity squared over oh, we can't do that. I guess we're going to do that. 100? I don't have enough room. We can't do 100. I did not plan this very well. Oh, I don't want to use the same numbers as before. We're using the same numbers. I'm so sorry. X plus 2 quantity squared over 25 plus y minus 5 quantity squared over 9 equals 1. Yeah, I'm sorry. I only have a 10 by 10 grid. I did not plan that well. If you would, please find your A, B, C, H, K. I'll give you a minute. So a squared is the bigger denominator. A squared is 25, so a is 5. B squared is the smaller denominator. B squared is 9, which makes B 3. C is given by c squared equals a squared, 25, minus b squared, 9, which makes RC 4. Questions so far? Okay. H is always with x. We have x plus 2, which is the same thing as x minus negative 2, because it has to be in this format, x minus h. So our h is negative 2. We have y minus 5, which is already in the format y minus k. So k is 5. So our center is negative 2, positive 5. Is this horizontal or is this vertical?
Horizontal.
Very good. It opens left and right. So we'll go left how many units and right how many units to find the vertices. Remember, A is the distance from the center to the vertices, so we'll go left and right 5 units. If we go left 5, we'll have one vertex at negative 7, 5. And right 5, we'll have another vertex at 3, 5. B will be the distance from the center to the covertices. So, and we move perpendicular, so we'll go down 3 and up 3. Those 4 black dots are enough to sketch the ellipse. And then to top off the sun date, from the center we'll go left and right 4 to find the foci. So if we have one foci right 4 units, so 2, 5, and left 4 units, negative 6, 5. The last little part of this section is just a comment concerning word problems. Basically, all the word problems for this section and the next are treated very similarly, and that is well, actually, it's the same as parabolas. Now that I think about it, you want to always make sure you're centered at the origin. So anytime you're doing any of the word problems in this section and the next section, make sure you pick the centered at the origin equations, because those do not involve h and k. So it really simplifies your work. Okay. Questions on ellipses? All right, very good. So that is 10.2. Let's talk about 10.3. 10.3 is hyperbolas. And we'll learn via a picture again. So we have similar definitions as with 10.2. A again is the distance from the center to vertex. B is still the distance from center to co-vertex. And C is the distance from, oh my gosh, the handwriting, from center to foci. However, we have a very big change, and that is the equations themselves. We'll start off with, again, centered at the origin. And then from those, we have the two categories, horizontal and vertical. I'll write them down, and then we'll discuss the change. Horizontal is x squared over a squared minus y squared over b squared equals 1. Vertical is y squared over a squared minus x squared over b squared equals 1. So recap. One variable squared, parabola. Two variables squared with the sum, ellipse. Now we see two variables squared with a difference, hyperbola. That's how you can tell just by looking at it which of the three you have. Now granted, on your test, it won't say graph with the equation. It'll say graph the hyperbola. So you'll already know that it's in a hyperbola, or you'll already know that it's an ellipse. There's that. However, with an ellipse, you knew, and I'm going to go back a slide, you knew it was horizontal or vertical based on where the bigger number was. However, for a hyperbola, there is no relationship between A and B. So the way you know if it's horizontal or vertical is which variable appears before the subtraction. If the x term is before the subtraction, it's horizontal. If the y term appears before the subtraction, it's vertical. Now you may ask, oh, what if they were rewritten? What if we multiplied through by g? They're always going to either be given to you as this, or what I forgot to do for the ellipse, we'll do, even though it's a video, I'd rather do it together just so we're comfortable. You can rewrite it to make it look like this. If you don't hear the words complete the square come out from my mouth in 10 minutes, remind me, because that means I forgot. But so we can do one together. But there's 2 videos of it anyways. So again, 2 variables being squared with a subtraction, hyperbola. If x is first, it's horizontal. If y is first, it's vertical. Now, as far as what a hyperbola looks like, we're going to go through an entire graphing procedure, and we'll do at least 2 more of these, just to make sure you are comfortable. Shrinky dink. Oh, good. now you can't even read it. Suppose we had x squared over... I'm so sorry. I just have to stick with 3, 4, 5. It's so boring. X squared over 9 minus y squared over 16 equals 1. Oh, there was one thing I forgot to tell you, and that was for a hyperbola, c squared equals a squared plus b squared. We do need that stuff. Oh, my EN didn't shrink down. Whoop, whoop. Oh my god. Oh my god. What's happening? It won't. Perfect. It's perfect. So same as before, we need an ABCHK. It's like the world's worst puzzle on Wheel of Fortune. Now, notice our equation in blue has the format of a horizontal because x is first. Because of that, notice that means that a squared is 9. Because the first term has the format x squared over a squared. If a squared is 9, a is 3. The second term has the format y squared over b squared, which means b is 4. So the idea of bigger denominator does not exist for hyperbola. Okay. Before we go any further, we're going to start with our a and our b. It's horizontal. Keep that in, oh, wrong slide. So keep that in mind. We're going to use this a and a b to graph a box. I think the box has a name. Steve. We're going to call it Steve. We're going to use the a and the b to graph Steve. How this works is because we're centered at the origin, which hopefully that's okay. H and k are both 0. We're not subtracting anything from the x and the y. How this works is moving horizontally a units. I'm going to put a point at -3, 0 and +3, 0. Which means we have a vertex at -3, 0 and 3, 0. So again, a is the distance from the center to the vertices. Moving perpendicularly, we're going to have our co-vertices, in this case up and down 4. So up 4 is at 0, 4, down 4, 0, -4. Unlike for an ellipse, the co-vertices are not actually part of the graph. The vertices are, but not the co. I put open circles for my co-vertices. You don't have to. I'm not going to be that particular. It's not to say the B is not important. It's still very, very important. So instead of drawing an ellipse like we would have done in 10.2, what we now do is we create a box. So we'll go up into the co-vertex, go over to the other vertex, go down all the way to the other co-vertex, go over to the vertex. You know how to make a box. So we have found Steve. The diagonals of this box create, and you didn't think you were going to ever hear this again, oblique asymptotes to the graph of the hyperbola. Oh my gosh. So from the center, go out to the corners of the box. Oh no. Oh. Do your best. Oh no. Oh, this is awful. Oh. All those years in art school wasted. Oh. So recap so far, we found our A, we found our B, we used the A and we found the center. We used the A, B, and the center to draw this box. Diagonals of the box form the oblique asymptotes to the graph of the hyperbola. We know this hyperbola opens left and right. Notice we have two directions this time because it's horizontal, and we know it's horizontal because the x is first. Okay. As far as the curves themselves, from the vertex, I'm going to start at -3, basically branch out towards the asymptotes. Something like that. And then same thing with this one over here. Start at the vertex, 3, 0, and branch out towards the asymptotes. It should look like a tree trunk. If you want to draw a Lorax, I forgot what Loraxes look like. I just know they're sad. All right. You can draw a Lorax, your choice. If you don't know what I'm talking about, read a book maybe. Seriously? Okay. All right. 2 more parts to go. And those parts are the foci. Foci is given by c. If c squared equals a squared plus b squared, then we'll have c squared equals a squared 9 plus b squared 16, which is 25, which means c is 5. Remember, c is the distance from the center to the foci. Foci must be inside the curve, and we have 2 curves here. And you go in the same direction as you did for the vertices, so in this case left and right. So if we go left 5 from the center, we get our first foci, which is at -5, 0. And if we go right 5, we get our second foci, which is at 5, 0. The last thing is the equation of these asymptotes. To be honest, this one's not terrible. And the reason it's not terrible is because notice our asymptotes go through the origin. Because it goes through the origin, then they'll both have the format y equals mx. The plus b would be 0, technically. Now, as a reminder, the way the book approaches things is totally fine, but they inundate you guys with formulas. I'd rather you just count. M, remember, is the slope, and remember, slope is rise over run. So notice here, to get the increasing line, this guy here, we want up 4, right 3. So that means that slope is 4/3. So the increasing line would be y equals 4/3 x. And for the decreasing line, notice we had gone down 4, right 3, which means that slope is -4/3. Hooray! So that is a hyperbola. And just as a comment in passing, any point you have on the hyperbola, if you found the distance between that point and each of the foci, but you subtracted those two distances, you'll get a number. And that's the same number if you compare it with any other point. So for an ellipse, every point was the sum of the distance, had the same sum from the distances. For a hyperbola, it's the difference of the distances, and that's sort of reflected in the equations themselves. Ellipses had a plus, hyperbolas have a minus. Okay, questions on this one? Okay, so let's write up our hyperbola equations. Again, these are given to you. They are written on Braille paper with a German accent, so good luck. You'll be fine. Horizontal hyperbolas, actually, let's write it all down. Centered at the origin is, you know what, I'll just write it down. So let's try one. We'll do a graph where it's not at the origin. I'm trying to think if we can get away with doing one. I would never give you one that's not centered at the origin that has a radical in it, because that would be awful. So I apologize. For one more time, we get a 3, 4, 5. It's going to be so boring. I'm so sorry. Suppose we had y squared over, what will this be here? We'll do 16 minus, nope, I lied to you. Suppose it was y minus 1 quantity squared over 16 minus x plus 2 quantity squared over 9 equals 1. And just so it's all on the same page, I'll write down the formula we're going to compare it to. I want you to carefully, as before, give me A, B, C, H, K. We'll do the graph together. What is A equal to?
Four.
Yep. B is equal to?
3.
Good. C?
5.
Yep. Because that's 4 squared plus 3 squared, which is 25. So C is 5. H, be careful.
Would that be -2?
Very good. H is always with X, K is with Y, K is 1. Which means our center is at -2, 1. What directions do we move for the vertices? The wheels on the bus go shame on all you all. Shame. The wheels on the bus go up and down, up and down, up and down. So we have a vertex at -2, 5 and -2, -3. Co-vertices go left and right, in this case 3 units. So we're at -5, 1, and 1, 1. Now that we have our vertex and our co-vertex, we can draw our box. And now that we have the box, we can draw in the line. Oh, that should be dotted. Oh, I'm not gonna. That took all my energy. All right, that should be dotted. I'm gonna undo that. Hey, Marsh. You want to say hi to everyone? You can say hi. There you go. We're doing hyperbolas today. We'll worry about the equations after. Not yet. So AB give us the box. Box gives us asymptotes. With that information, we can sketch in the curves themselves. Remember, oh, that's awful. Go to the start of the vertex and branch out towards your asymptotes. The foci go in the same direction as the vertices, so in this case up and down, and we'll go up and down 5 units. So from the center, if we go up 5, we'll be at -2, +6, and down 5, -2, -5. It should be -4. Yeah, it should be -4. Sorry about that. All right, the last little bit of noise is the equation of the asymptotes, which takes us back to chapter 1, because you're finding the equations of lines, which means you need a point and a slope. Well, here's the deal. You can make your life a little bit easier. Remember point-slope form, y minus y1 equals m times x minus x1. Both of the blue lines have to go through the center, and remember the center was HK. So we'll have y minus 1 equals m times x plus 2, because it's x minus negative 2. So it's just the m we don't know right away. Well then, think about rise over run. For the increasing line, notice we went up 4, right 3. So that one has a slope of 4/3. And the other one, we went down 4, right 3. So that one has a slope of negative 4/3. So then all you would do, I'm not going to do it, you can do it, is for both of these equations, you would just solve for y and write it in slope-intercept form. So distributing the slope and bringing that one over. But that's the main trick, is just use your point slope, and remember that your HK is a point on the line, and that saves you a lot of time. Okay. The last thing to mention for hyperbolas is I had mentioned completing the square, and that's going to be used when, for instance, it's not written in the format that's given to you right there. It's written in another way, and it's going to look like I didn't prepare this, so it looks like I'm just, I don't know, putting this into a program right now to make it look like I'm coming up with an example off the top of my head. I mean, I would never ever do that to you guys, to where I'm just making something up without actually practicing it. That'd be pretty awful of me. So as I continue to delay here, oh look, I'm done. Okay, so suppose we had 25x squared minus 100x minus 144y squared minus 864y minus 1196 equals 0. Truth be told, I may have made a mistake. We'll figure it out later. So you might have the directions that say find the center, find the vertices, foci, blah, 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 but it looks like this, which is, as people would say, crazy talk. So the way you get it into the formats that we're used to, namely something that looks like these guys, you have to complete the square. So I just want to do this real quick, just refresh your memory of completing the square. So to complete the square, two things have to happen. The variables have to be by themselves, and the leading coefficients have to be a 1. We have technically two leading coefficients because we have an x squared and a y squared. So what we'll first do is we'll get the variables by themselves. The gap is intentional. And I'm going to move that 1196 to the other side. Notice from the x terms, I could factor out a 25. Gap is intentional. From the y terms, I could factor out a negative 144. Boop. I think that's 6. 864 divided by 144. I did it right. Is 6. So the variables are by themselves, leading coefficients of 1. We are prepped to complete the square. So to remember to complete the square, you take half of the linear coefficient. Half of -4 is -2. Squared is 4. So we add 4 inside of those parentheses. However, we do not add 4 to the right-hand side, and the reason being is because that 4 is in a parentheses that is being multiplied by 25. So to balance out this equation, we actually have to add 4 times 25, which is 100. Because if we distributed that 25 through, we actually added 100. Likewise for the y's, the linear coefficient is 6. Half of 6 is 3, squared is 9. So to complete that square, we would put 9 inside. -144 times 9, I don't know. I have no idea. Yeah, I totally botched this, everyone. This should end with should be a different number over here. But let's just play along and pretend I know what I'm talking about. -144 plus 9 is -144 times 9 is -1296. So what happens is on the left you'd have 25 equals x squared minus, I'm sorry, let's do it this way. On the left you'll have 20, that should be a 6 over here. 25 times x squared minus 4x plus 4 factors as x minus 2 quantity squared minus y, I forgot my squared here, everyone. Y squared plus 6y plus 9 factors as y plus 3 quantity squared. And I'll tell you what should have happened, and it totally didn't happen. So I'm so sorry. On the other side, there should have been a number here. This unfortunately equals 0. I should have made it work out so that it equals 3,600, and I'll tell you where the 3,600 came from. So, oh, you know what we can do? We can say, instead of 0 here, we can sneak in 3,600. Look, nobody knows. It was there the whole time. So this would have been what, 4796? I don't know. I can't do math. Anyways, pretend that this equaled 3,600. Let's just go with that. Like it equals 3,600. All right, good. This is why you prepare. And then we need this thing to equal 1 on the right-hand side. So the way you would do that is you would divide both sides by 3,600. Uh, 25 over 3,600 is 144 downstairs. And 144 over 3,600 is 25 downstairs. So you can probably see where those numbers came from now. So now it's in the format that we wanted to get into. If there wasn't that oops. Oh well. So yeah, if it's in this format, boop boop, you just have to complete the square twice. Once for the x's, once for the y's. All right, that's 10-3. The last part, our last section, is 10-4. Systems of nonlinear equations and inequalities. Really no theory here. This is all just example after example. Let's first start off with the nonlinear equations. You're going to have two types. And I apologize. Oh. There you go. Suppose we had that works. X times y equals 4 and x plus y equals 5. So the second equation is technically linear. The first one is not. The first one is actually your reciprocal function that we had so long ago. And the two ways you are allowed to solve these are stuff that you learned in 0965. You're allowed to do substitution and you're allowed to do elimination. Sometimes both processes are fine. Other times only one is the better way to go. Because we don't have a like term in both equations, we have an x times y in the first and an x plus y in the second. Elimination wouldn't really be helpful here. Substitution is totally fine. And remember, in the process for substitution, you pick an equation and you solve for one of the variables in that equation. So for instance, in x plus y equals 5, that'd probably be easier to solve for a variable. We can solve for x, for example, by subtracting y from both sides. And remember, in the process of substitution, you take that expression for x and put it in for the same x in the other equation. So instead of x times y equals 4, we'd have 5 minus y times y equals 4. Which is the same thing as 5y minus y squared equals 4. If we brought everything over to the right and rearranged terms, we'd get y squared minus 5y plus 4 equals 0. And how does that factor? What multiplies to positive 4 but adds to negative 1?
Negative 5 and 1.
That would multiply to negative 5. So because this is a plus sign, these must both be this sign, so y minus y minus. So we would use 1 and 4. Negative 1 times negative 4 is positive 4. Negative 1 plus negative 4 is negative 5. Good. What does that say about y?
It equals 1 and 4.
Yeah. Good. Well, we need to solve for x. Well, we previously said that x was 5 minus y. If y was 1, x would be 5 minus 1, which is 4. And if y was 4, x would be 5 minus 4, which is 1. Huzzah! We have two ordered pairs. When x was 4, y was 1. And when x was 1, y was 4. So unlike your systems of equations that we did in 9.2 and 9.3, where you only had one solution, here it's possible to have a bunch of solutions. So that's an example of one that needs substitution. You could also have ones that need elimination. Oh, I don't know what I just did. I went to that one. So let's suppose we had x squared plus y squared equals, I don't know, let's say 18. And x squared minus y squared equals, now hold on, because you're asking a lot for me right now. Oh my gosh. How in the heck do I want to say 14? I think we're going to go with 14, everyone. It's half. We did 14. All right, equals 14. What's the first equation, by the way? If you were to graph it, what would it look like? Rhymes with circle. Very good. It's a circle. What's the second one? Rhymes with hyperbola. Very good. It's a hyperbola. You guys are awful at rhyming. Seriously. Okay. This one's great for elimination. Substitution is not recommended because all the variables have a square. If you were going to solve for any of the variables, you'd have to take a plus or minus square root, which is really, really ugly. Elimination is much better. In fact, if we just add up the equations, notice that the y term goes away. But just be careful. X squared plus x squared is 2x squared. Students sometimes write x to the fourth. You're not multiplying, you're adding. On the right-hand side, we get 32. So if 2x squared equals 32, that means x squared equals 16, which means x equals what? And?
4.
And?
3.
No.
Negative 4.
There you go. Plus or minus 4. Good. So now that we found x, we have to back substitute to figure out what y is. We can go back to either of the original equations and put in our value for x. if we put in 4, I'm going to use the first one because it's a little bit easier. If I put in 4 in for x, I'd get 4 squared plus y squared equals 18. 4 squared is 16. So if I subtract 16 from both sides, I get y squared to be 2. In taking a square root, remember when you square root an equation, you include a plus or minus. So this occurred because x was 4. So this gives us 2 ordered pairs for square root of 2, for negative square root of 2. We might go over by a couple minutes. Same deal, put in negative 4 in for x. Negative 4 quantity squared is also 16. Bringing that over, you get 2 again. So you again get plus or minus the square root of 2. But these guys occurred because x was negative 4. So this one had 4 solutions. And as far as why that should make sense, the first one was a circle. The second one was a hyperbola that was horizontal. And notice, I mean, this is a very rough sketch. I didn't do the A, B, C thing at all. But notice when a hyperbola intersects a circle, it is possible to get 4 points, and that's what we have. It's possible to get 2 points. It's possible to get no points. We happen to get 4 points. All right. So there's your options, elimination or substitution. The last one, the last thing to talk about is the inequalities. I'm just going to make this up real quick. We'll make it 20. We'll make it 36. Make it exciting. And we'll have y. Now, no idea. Let's find this out together. So, in your system of nonlinear inequalities, it's very similar to your system of linear inequalities, which was an 095 topic. We'll go through each one. The first one we'll do in purple. Boop. Most of the work actually happens off to the side. The big thing you got to do is the very first step, which is to graph the related equation. So ignoring the inequality, you graph the related equation. X squared plus y squared equals 36 is a circle of radius 6. Oh my gosh. How am I going to do this? Why did I pick such a big number? Tina Belcher. I'm proud of that. I'm going to have a cookie later. So step 1, graph the related equation. Comment, because there is an equal sign on the inequality, it's less than or equal to, I used a solid curve. If it were not an equal to, you would use a dotted curve. The next step is to pick a point that is not on the line, it's on the curve itself. 0, 0 is a common option. So if I picked 0, 0, which is inside the circle, I would, off to the side, put in 0 in for x and 0 in for y. And I would ask myself, is that true or false? Does 0 squared plus 0 squared, is that less than or equal to 36? Yep. So here's the deal. 0, 0 is inside the circle. The point 0, 0 represented all points inside the circle. And we found that all points inside the circle make it true. So you always shade the true part. So we're going to shade inside the circle. Hopefully it's easier for you, because that was a near nightmare. Great. The next one I'm going to do in this peanut butter color. Again, ignore the inequality. Graph the related equation. Notice this guy is a parabola moved down 2 units. So all your other equations are fair game in this section. So that guy will look something like this. Whee! Yee-oo! So draw your curve is the first step. Second one is pick a test point. We can pick 0, 0 again because it's not on the parabola itself. If I put in 0 in for x and 0 in for y.
I'm sorry, what was the second step?
Pick a test point. So I picked 0, 0. Marsh, come here. Good boy. If I put in 0 in for x, 0 in for y, is this true or false? Hi.
False.
False. Because this is false, and 0, 0 came from inside the parabola, that means all points inside the parabola are false, which means all points outside of the parabola are true. So all these points out here are true. Now there's no algebraic way to write your answer. You don't say x equals 5, for example. Instead, it's all about the graph. So we need to be inside the circle but outside the parabola. So that means this shape here, I don't know. It looks like Mario's mustache when he's very happy. This shape is your final answer. So any point in this region will make both inequalities true at the same time. Hooray! Congratulations! That's 1530!